In last class, in exercise number 1.1, we completed first bit, second bit. In this class, we are going to complete this third bit and fourth bit. See, they given one relation here. We need to check this relation is reflexive, symmetric, trans to. Okay. We need to check this relation satisfies which condition. You see, this is the given question. As usual, in this first question, for all the bits, first we'll write three steps. First one is relation is on which set. If you observe, this relation is on this set A. So, I written set A. Second step is relation is on which set. They given that R is a relation in set A. They mention that R is a relation on A. That means that R is a relation from A to A. That means that R is a subset of A cross A. And main important thing is how the relation is defined. They define relation like this. R equal to order pair x comma y such that y is divisible by x. Okay. Before going to continue this further, you need to know about A cross A because all these order pairs are from A cross A. A cross A. A cross A contains what elements? You look here. A cross A. A is 1, 2, 3, 4, 5, 6 cross 1, 2, 3, 4, 5, 6. A cross A contains what elements? You tell 1, comma 1, 1, comma 2, 1, comma 3, 1, comma 4, 1, comma 5, 1 comma 6. I hope you are understanding. Take 1, you pair with all the elements of this, right? Similarly, next you take 2. What you will get? 2 comma 1, 2 comma 2, 2 comma 3, 2 comma 4, 2 comma 5, 2 comma 6. Next, take 3. 3. Take 3. 3 comma 1, 3 comma 2, 3 comma 3, 3 comma 4. Like that, it is not a good idea to write A cross A 36 elements. So, but keep in your mind that what are there in A cross A. Okay, based on that, we are going to write this relation. Okay, now I'll write this relation in roster method. Actually, this is in set builder method. I list what elements are there in this relation. You know that all the elements order pairs comes from A cross A. A cross A first element is what? A cross A first element is order pair 1 comma 1. I'll take 1 comma 1. Now I'll check that this 1 comma 1 is there in this relation or not. 1 comma 1 will be present in this relation when y is divisible by x. You see, this is x, this is y. Here y is 1. Y is divisible by x. Here 1 is divisible by 1. Yes, we know that 1 is divisible by 1. So order pair 1 comma 1 belongs this relation. Okay. In A cross A, first element is 1 comma 1. In A cross A, what is the second element? In A cross A, second element is 1 comma 2. In A cross A, second element is 1 comma 2. Now, is 1 comma 2 belongs this relation or not? See here, 2. Y means 2. Here, 2 is divisible by 1. You check that 2 is divisible by 1 or not. 1 in this 2 times. Remainder is 0. As we are getting remainder 0, we can say that 2 is divisible by 1. That means order pair 1 comma 2 is there in A cross A and order pair 1 comma 2 is satisfying this condition. So order pair 1 comma 2 belongs this relation. I hope you understand. In A cross A, next element is 1 comma 3. Now you take this 1 comma 3. 1 comma 3 belongs this relation. You check. In place of y, you write 3. Here 3 is there. 3 is divisible by, in place of x, you write 1. Is 3 is divisible by 1? You check. Is 3 is divisible by 1? Yes. 3 is divisible by 1. You can easily say that 3 is divisible by 1. Similarly, in A cross A, next element is 1 comma 4. 4 is divisible by 1. Similarly, 1 comma 5, 1 comma 6, 1 comma 7. Can we write 1 comma 7? No, you cannot write 1 comma 7 because in A cross A related to 1, here you'll write like this now 1, 2, 3, 4, 5, 6. Last element is what? 1 comma 6 only. 1 comma 7 does not belong to this relation. Now in A cross A, next element is what? Next element starts like this 2 comma 1, 2 comma 2, 2 comma 3, 2 comma 4, 2 comma 5, 2 comma 6 like that. 2 comma 1. You take 2 comma 1. 2 comma 1 is there in A cross A. Now you need to check this 2 comma 1 is there in this relation or not. When 2 comma 1 belongs this relation, when y is divisible by x, that means 1 is divisible by 2. In place of y you write 1. Is 1 is divisible by 2? Is 1 is divisible by 2? See, actually 1 is divisible by 2 means 1 by 2. 1 by 2 is not an integer. You are getting 0.5. You can easily say that 1 is not divisible by 2. That means order pair 2 comma 1 does not belong to this relation. Next, after 2 comma 1, what element will be there in A cross A? That is 2 comma 2. 2 comma 2 is there in A cross A. Now we will check that 2 comma 2 satisfies this condition or not. In place of y 2, in place of x also 2, right? Is 2 is divisible by 2? Yes, 2 is divisible by 2. 2 by 2 is 1. It is an integer, right? Yes, 2 comma 2 belongs this relation. Now like that you need to check every element in A cross A. 2 comma 3, 2 comma 3 does not belongs this relation, because when we check for 2 comma 3, look here, 2 comma 3, 3 is not divisible by 2. 3 is not divisible by 2 because 3 is odd number. Next, after 2 comma 3, 2 comma 4, is 4 is divisible by 2? Yes, 4 is divisible by 2. Next, 2 comma 4 is over. Next, 2 comma 5, is 5 is divisible by 2? No. Next, 2 comma 6. I hope you are understanding. 3 comma 1, no. 3 comma 2, no. 3 comma 3, yes. 3 comma 3 is there in A cross A. This 3 is divisible by 3. Okay. Next, 3 comma 4, no. 3 comma 5, no. 3 comma 6, yes, because 3 comma 6 is there in A cross A and 6 is divisible by x. Okay. Now 4 comma 1, no. 4 comma 2, no. 4 comma 3, no. 4 comma 4, yes. 4 comma 4 is there in A cross A. 4 is divisible by 4. Okay. Next, 4 comma 5, no. 4 comma 6, no. Next, 5 comma 1, no. 5 comma 2, no. 5 comma 3, no. 5 comma 4, no. 5 comma 5, yes. 5 comma 5 is there in A cross A. 5 is divisible by 5. Next, 5 comma 6, no. 6 comma 1, no. 6 comma 2, no. 6 comma 3, no. 6 comma 4, no. 6 comma 5, no. 6 comma 6, yes. 6 comma 6 is the last order pair in A cross A and 6 is divisible by 6. Okay, right. Now I written this relation in roster method. It is not compulsory to write these elements because this is a bigger set. If you write it, you can easily check. Okay. Now I need to check that this relation is reflexive or symmetric or transitive. All those things I need to check. Okay. Okay. Reflexive. How to check reflexive? What is the definition of reflexive? For every x in set A, order pair x comma x is there in the relation or not. That we will check. Okay, right. You take 1 in set A. For 1 in set A, 1 comma 1 is there in A cross A? Yes. For 2 in set A, 2 comma 2 is there in A cross A? Yes. For 3 in set A, 3 comma 3 is there in A cross A? Yes. For 4 in set A, 4 comma 4 is there in A cross A? Yes. For 5 in set A, 5 comma 5 is there in A cross A? Yes. For 6 in set A, 6 comma 6 is there in A cross A? Yes. So what happened here? For every x in set A, order pair x comma x is there in this relation. So I can say that this relation is reflexive. I hope you understand. So how you will write the answer? You need to write like this. For every x in set A implies order pair x comma x belongs to the relation. From this we can say that the relation R is reflexive. The relation R is reflexive. I hope you understand this. Now we will check symmetric condition. What is symmetric definition? For every order pair x comma y in the relation, y comma x also must present in the relation. Okay. Now you know that. See, this is the relation. This relation I'll check for every order pair. 1 comma 1 is there. For this type of elements, 1 comma 1, 2 comma 2, 3 comma 3 always satisfy symmetric condition. Okay. Now you come to this 1 comma 2. For 1 comma 2, 2 comma 1 is there in this relation. You check, is there anywhere 2 comma 1? 2 comma 1? No. That means for the order pair 1 comma 2, 1 comma 2 is there in the relation, but 2 comma 1 doesn't belongs this relation. So for the order pair 1 comma 2 is there in the relation, but the order pair 2 comma 1 does not belongs to this relation. So we say that this relation R is not symmetric. I hope you understand. Now we'll check transitive condition. How to check transitive condition? For this problem, we can do the solution in two methods. One is verifying by taking every order pair x comma y comma z exist or not. For x comma y comma z, x comma z exist or not. That is one procedure. Another procedure is directly by taking this condition, we can write transitive. So we'll do that method instead of checking, because here so many order pairs are there. Checking like that, it takes so much of time. So let's see how I'll do this problem. I'll take there exists an order pair x comma y and y comma z in the relation. If I suppose x comma y is there in the relation, that from the relation it says that y is divisible by x. If I say x comma y is there in this relation, this says that y is divisible by x. So this tells you that y is divisible by x, and here y comma z belongs this relation. This tells you that z is divisible by y. Z is divisible by y. Here you need to know few basic things. If y is divisible by x, suppose 4 is divisible by 2. If 4 is divisible by 2, 4 can be written as multiple of 2. 2 into 2, 2 into some integer. This is integer. Please try to understand. This is some integer. As y is divisible by x, what thing you need to know that y is multiple of x. I'll write here y into k1. Here k1 is what? K1 is an integer, right? And as we know z is divisible by y, z can be written as multiple of y into some integer. Okay. Now what I need to look, I need to look that x comma z is there in the relation or not. When I can say x comma z is in the relation, when I say that z is divisible by x. When I can say z is divisible by x, if z can be written as multiple of x into some integer. If z can be written as x into some integer, then I can say that z is divisible by x. Okay. So what I'll do here, first I'll write this z is equal to, what is z? Z is y into k2. Z is y into k2. Now you observe this further. Here y is there now, that y can be written as x into k1. Okay, then this is x into k1 into k2. Here what is k1? K1 is an integer. What is k2? K2 is an integer. So what I can write here, x into, if I multiply these two integers, again I'll get an integer. So I'll write it as k3. What is k3? Where k3 is the integer that we'll get when we multiply k1 and k2. So what the point here you need to observe, here I got z as a multiple of x. Z can be written as multiple of x. This itself indicates that z is divisible by x. If z is divisible by x, then what I can write? I can write that x comma z belongs this relation. When x comma y, when x comma z belongs to R, if z is divisible by x now. So what happened here? If such type of order pair exists, then we came to know that x comma z also belongs this relation. Another method is also there in the beginning of definition of transitive relation. I check a transitivity with the help of every element. Like that also you can check and you can say, you can write the answer. But this is a better way of writing the solution of transitive for this relation, right? So for x comma y belongs to R, y comma z belongs to R, I got that x comma z belongs to R. Then I can conclude that therefore this relation R is transitive. Here we'll conclude. This is the first one we got, this is the second one we got, and this is the third one. So from this 1, 2, 3, we came to know that the relation R is reflexive and transitive but not symmetric. I'll write the same thing. The relation R is reflexive and transitive but not symmetric. So this is the conclusion we given, that this relation is reflexive and transitive but not symmetric. I hope you understand this solution. This relations and functions concept actually easy, but this for particular problems, when we do the problems, a little bit of confusion will arise in your mind. That confusion you can clear only with a good knowledge on theory part. And moreover, as slowly started doing problems like this, at particular point you will come to know that yes, this relations is easy. Now you observe this fourth bit. We need to check this relation is reflexive or symmetric or transitive. Before going to that, we'll write what are the 3 points we need to observe from this question. First point, this relation is on which set? This relation is on set Z. So I'll write Z. What are integers? 0, plus 1, minus 1, plus 2, minus 2, plus 3, minus 3. These are the integers. Second point is R is a relation on what set? They given in the question that R is a relation on Z. R is a relation on Z. It means that R is a subset of Z cross Z. R is a relation on Z. It means that R is a subset of Z cross Z. Third one is how the relation is defined. Third point is relation is defined as order pair x comma y such that x minus y is an integer. So these 3 points in every problem of first question we are observing first and then writing. Okay. Now we need to check this relation is reflexive or symmetric or transitive. As Z is an infinite set, Z cross Z is also infinite set. So writing this relation in roster method like 1 comma 1, 1 comma 2 like that, it's not a good idea. Actually, it is not possible to write actually because this is R is also infinite set here. You observe R is a relation given like this. Na? It tells you that X is what? X is an integer. What is Y? Y is also an integer. Which order pairs belongs this relation? You take two integers such that difference of them is an integer. For example, 2 is integer, 3 is integer. What is difference of them? 2 minus 3 is minus 1. Minus 1 is integer or not? Yes, minus 1 is an integer. Like that, if you observe, this R contains infinitely many ordered pairs, right? So best thing is generally by taking these points, we'll try to check reflexive symmetric transitive without writing this relation into roster method. Reflexive relation. We need to check this is reflexive or not. Okay. What is reflexive condition? For every x in Z, here Z is there na? For every x in Z, order pair x comma x is there in the relation or not. That we'll check. Okay. Here, when order pair x comma x belongs to the relation, if x minus x is an integer, x minus x is what? X minus x is 0. 0 is an integer? Yes, 0 is an integer, right? So here, for every x in integer, you take any integer, we can say that x minus x is 0. 0 is an integer. Whatever integer you take 2. 2 minus 2 is 0. You take minus 2. Minus 2 minus of minus 2. That is 2 plus, that is minus 2 plus 2. That is 0. Right? You take any integer, integer minus same integer, x minus x is 0. Right? As x minus x is an integer, from this I can say that x comma x belongs to relation. So what happened here? For every x in Z, order pair x comma x belongs to relation. So I can write that the relation R is reflexive. Now, this relation R is symmetric or not. What is symmetric? For every order pair x comma y in the relation, if the order pair y comma x also belongs to the relation, then we say that relation is symmetric. Now what I'll do, I'll take one order pair from this relation. You take x comma y in the relation R. If x comma y is there in the relation R, it indicates that, as per the definition, if x comma y is in the relation, it indicates that x minus y is an integer. As I taken x comma y in the relation, I can say that x minus y is an integer. Okay, x minus y is integer. Suppose x minus y is 2. If 2 is integer, minus 2 is also integer. You suppose x minus y is minus 4. Okay, then minus of minus 4. that is also an integer. What I am trying to say, if x minus y is integer, then minus of x minus y is also an integer. If x minus y is integer, minus of integer, suppose minus 4 is there, minus 4 is an integer, minus of minus 4 plus 4 is an integer. Minus of x minus y is what? Minus of x minus y is y minus x. So here we got that y minus x is an integer. As per this relation, when I can say that y comma x belongs to this relation, when I can say y comma x belongs to this relation, if y minus x is an integer. So here what I got that y minus x is an integer. From this what I can say? I can say that the order pair y comma x belongs to the relation. So what happened here? For every x comma y belongs to R, y comma x also belongs to R. So I can conclude that the relation R is, therefore the relation R is symmetric. How to check transitive relation? What is transitive relation? For every order pair x comma y belongs to R and y comma z belongs to R, we look for x comma z belongs to the relation or not. So first I'll take x comma y belongs to R and y comma z belongs to R. This tells you that x minus y is an integer. Y comma z belongs to R. This tells you that y minus z is an integer. I'll write the same. X minus y is an integer. Y minus z is also an integer. So here what I need to check? I need to check x comma z belongs to the relation or not. I need to check that x comma z is there in the relation or not. It means that when x comma z belongs to R, if x minus z is an integer, if x minus z is an integer, then I can say order pair x comma z belongs to the relation. You know, addition of two integers is again an integer. Here I know that x minus y is an integer, right? Now I'll add x minus y and y minus z because y minus z is also an integer. You know, sum of two integers is again an integer. So here you see this minus y plus y will get cancelled. Then what you will get? You will get that x minus z is an integer. If x minus z is an integer, what I can write? I can write that order pair x comma z belongs to R. When you came to know that x minus z is an integer, I can say that the order pair x comma z belongs to R. That means what happened here? For every x comma y comma z in the relation, x comma z also exists in the relation. From this, I can write that this relation is transitive. So we came to know that this relation is reflexive. I'll take it as 1. And this relation is symmetric. I'll take it as a second point. And this relation is transitive. You take it as a third point. From 1, 2 and 3. What you can say, as this relation is reflexive, symmetric, transitive, I can say that R is equivalence relation. Therefore, the relation R is a equivalence relation. I hope you understand this first 4 bits in exercise number 1.1.